Um, okay, so what I want to try to do to motivate the talk is to start from the perspective that when we get together to communicate with each other, we're not just moving one token at a time or one turn at a time. There's some kind of goal that we have in mind. I guess the keynote this morning maybe should inspire us to be a little concerned about goals that language models have, but here we're going to try to focus on ways in which humans and language models can work together to achieve goals. And in doing that, in trying to achieve goals in conversation, there are a number of capabilities that we have to bring to bear to do that. So, we have to track the state of the conversation. We have to maybe make some plan towards some state that we're trying to achieve. There's something I'd like you to know, or something I'd like to learn from you, or some project I'd like us to engage in together. We may have to introspect about what we know, or try to make inferences about the beliefs and goals of others. And I think these are aspects of language that I think are still, relative weaknesses of even the strongest language models that we have. So why is that? Why are these weaknesses? I would argue sort of the current, sort of mainstream paradigm we have for building language models now is not really well suited to teaching these kind of conversational skills. So at pre-training time, we can sort of do imitation learning on zillions of successful conversations, but I think that's of limited use because the participants in those conversations, they're conditioning on some background knowledge that they have that's different from what the language model might have when it's in conversation with you. And so that's information that's not really available. In post-training, like RLHF and even instruction tuning, these are typically single-turn scenarios, so that's kind of a relatively weak signal for effective conversational planning. What we propose in this paper is an alternative post-training strategy that we call collaborative self-play. So if our goal is to learn to work together with language, we should try to teach it that way by building multi-agent communicative scenarios with goals that require effective communication to succeed. So that sort of require, on the way, execution of these conversational abilities that I showed on the previous slide. Let me make this much more concrete by talking about a specific example, and this is the example we built on in the paper. So the setup here is information provision. So there's some question that a user has, and it's presented then to a language model agent, agent A, and that agent then has the ability to pass that question to helpers. And the helpers are distinguished by having knowledge resources that are unavailable to agent A. So helper B has access to Wikipedia, helper C has access to PubMed, which is a corpus of biomedical abstracts and papers. And they can use those corpora if they want to, or they don't have to. And then they can pass information back to agent A, who then integrates all that information, maybe uses its own knowledge, and finally passes information or an answer back to the user. And so we can run a little rollout like this. We sort of express what these agents are doing through these, just like a small set of discrete actions. So agent B can execute the search action and then get some retrievals. And then agent B can mark its answer as a hedge if it's not confident in the answer. And agent C could mark its answer as an answer. That means that it is confident. So just a little binary signal of confidence. And then the group as a whole is rewarded for accuracy, and it's penalized for the number of tool calls that it makes. So this is the setup that we're going to run at training time. So we don't prescribe exactly what agent B or C should do at any point in time. We just say that the reward is to give good answers. And then at test time, what we're going to do is evaluate the individual helper agents. And what we hope is that they've learned by playing this game to use tools in exactly those cases where tools are helpful, to mark answers as confident when they're likely to be correct, and to mark them as hedges where they're likely to be incorrect. Okay, so why should this work? So I'll give you first an intuitive argument. As I said, the reward is for correctness with an effort penalty. The key sort of bit here, and you can sort of see another rollout on the right. This is a little question about Montreal. The key bit here is that the two agents don't get to reveal their identity to the asker. So the asker agent can't learn, oh, agent B is good at answering questions about general world facts or something that might be in Wikipedia, and agent C is good at answering questions about like biomedical science. It just has to, you can sort of see in the bottom like block here, the only information it has when it has to integrate conflicting evidence is that one agent marked itself as an answer and the other one marked it as a hedge. And so, in this rollout, it sort of successfully chooses the correct answer because the confidence markers were used correctly. And so again, the idea is to sort of distill the signal into a single policy for all the agents. So that's sort of the intuition. In fact, like we can do like more than just this kind of intuitive perspective, though. We can analyze this game, analyze the setup formally. It's actually not exact, it's sort of a stylized version of the game that's more amenable to analysis, where we sort of combine the two choices, whether to use your tool or not, and whether to answer with confidence or not. So, but this sort of stylized game, I think, will reveal something about when this setup can work. So in the stylized game, one possible action is S, which is to search and then answer with confidence, and the other one is G, which is to guess and then answer with low confidence. And the way this formal game works is that if player I plays the S action, then it has probability of being correct, alpha I. And if player I plays the S action and player J plays the G action, player I's answer is the one that we go with. And so the overall group's chance of correctness is alpha I. The chance of being correct if you don't use the search tool and you play action G is this beta, which typically, for it to be interesting, should be lower than at least one of the two alpha values. The tricky case is when both players play the S action. So they both are now saying that they're confident. And so what we imagine happens here is that the asker just like flips a fair coin and selects one of the answers at random. And so we get this alpha bar, which is just the average of alpha 1 and alpha 2. And this is a distinction from the game that we actually implement, but for analysis, there's these costs for playing the S action, for using the search tool, and the difference is that those are applied only to the individual agents here. So what you get if you've sort of seen any sort of game theory, you get this payoff matrix where you see for each configuration of actions, the payoff for agent 1, comma, the payoff for agent 2. And this is a special case of a really sort of classical game theory example called public utility provision. There's some utility that would be like helpful for everyone to have, but someone has to pay for it. And in this case, the utility is like the information that you get by doing search, and like, who should pay for it? Like probably you would want the agent whose alpha value is higher to pay for it. That would be the ideal situation. So we can analyze this game, and we can analyze the equilibrium conditions of the game. So these are the configurations in which neither agent can improve its individual reward by changing its action. And so we can have a theorem that says basically you can have a unique pure strategy equilibrium, meaning that there's just a single pair of actions that has this property that neither agent can improve its reward by deviating under the following conditions. So either alpha 1 is like really good, so like alpha 1 is higher than alpha 2 by more than twice the effort penalty, then you're in this upper left region, or the parallel situation here is in the lower right region, or like both of the alpha values are low, right? So here, the first agent's tool is so useful, like clearly it should be the one provisioning the information. Here, neither tool justifies tool use, right? So the only time you get in trouble is in this region here in the upper right, where both tools are fairly useful. And the reason I say you get in trouble is because you have multiple equilibria here. So you could sort of settle on the case where the agent with the less effective tool is nonetheless doing the search action. And neither agent can improve its reward from deviating from that equilibrium, but it's a suboptimal equilibrium. But I think the take home, for like the implementation is that what you want is an instantiation of the game where like the tools are really different from each other. And one agent, for each question, one agent sort of clearly has the best tool, and the gap is enough to justify the effort penalty. Okay, so like moving to the more empirical part of the paper, when we implement this, as I've sort of indicated already with the examples, we have these two helper agents, one that can search in Wikipedia and one that can search these PubMed abstracts. we can look at two data sets, like PopQA is kind of a data set about, a QA data set about like popular entities. It's pretty amenable to Wikipedia search. When you use Wikipedia search, your F1 is like much higher. BioAsk is like a set of questions that are kind of amenable to these PubMed retrievals. And when you do PubMed retrieval, you know, your F1 is much higher. So these kind of, the setup kind of matches the conditions identified in the theorem. Okay, so we take this game, we implement it by a procedure called reward self-training, which is essentially an approximation to reinforcement learning that we apply on top of GEMMA 2 9b. So for each data set, we have 1,000 questions. We do 32 multi-agent rollouts. On these 1,000 questions, we select successful rollouts, meaning ones that have high reward. We use those for fine-tuning, and then we iterate. So we update the policy and we do it again, and we do this 3 times. Okay, so on to results. The first thing I want to show, I think is maybe not the most interesting, but this is just the first question one should ask, which is about the cost-accuracy trade-off. And here we're going to compare this collaborative self-play procedure, again, learning by playing this game, in context learning, which, in general just searches pretty much on every question. We weren't able to get it sort of off of that behavior with the prompt. And then an alternative that we call action supervision, which is kind of like a special case of process supervision from the reasoning literature. Here, so for each agent, we basically try to design training data where, like, in the training set on exactly those cases where search is like better than no search by a significant margin, we train it to do search. On those cases where search doesn't help that much, but parametrically can get a good answer, we train it to give, a confident answer, and otherwise we train it to hedge. And so, similar to the relationship between process and outcome supervision, this assumes kind of more information than we have available in collaborative self-play. Collaborative self-play is really more of an outcomes supervision type story. And then we evaluate on these in-distribution data sets. These are, the same data that we use, the same data sets that we use for training, obviously a different split, and then 2 out-of-distribution data sets. And so, as I said, in-context learning is not only doing too many searches, but it's like less accurate because getting bad search results actually like makes the accuracy worse. Let me move ahead. Is it 1 minute? Is it? Okay. I think like the more sort of interesting aspects of the eval first is like knowing when like it's really helpful to use the tool. And so we can do an evaluation where we sweep over different search rates. So this is essentially ordering all the queries by the model's like probability of wanting to search. And collaborative self-play is the most effective at teaching like which are the examples that are most amenable to search. Like we're just sort of looking at the cost accuracy trade-off in a different way here. And then finally on this point about learning to hedge, so learning to distinguish when to use the answer action versus the hedged action. Again, we can sort, here we're just going to focus on like parametric knowledge, so we can sort the questions by P answer versus P hedge. And this is sort of exactly the sort of setup that action supervision is training, so it's not surprising it does well here, but collaborative self-play is also quite effective. And both are giving significant boosts over in-context learning. Oh, like one sort of really key point about this slide, and then the next one's my conclusion. We do this ablation here where, I mentioned anonymization as an aspect of the game, where the asker agent doesn't get to know who the helpers are. So we can modify the game, which is varying sort of one token, which is providing the identity of the helpers to the asker. And that sort of completely breaks the mechanism and causes it not to learn to hedge properly, because the asker can just learn who's likely to be accurate on each question, and there's no incentive to learn to be calibrated. So I really am on my last slide. I liked this picture that I think the organizers made, but what I want you to sort of leave with is this message that, like reasoning, conversation also is a goal-directed activity. And so, maybe we should think about language model training as, at least in part, like learning to achieve conversational goals, not just to mimic human conversations. When you start with that perspective, I think you realize like there are many types of conversations that we have, many other types of conversational skills that go way beyond like hedging, or not hedging. And so I think there's a lot more that you can potentially learn. So I'd like to see, a lot more work, of this style in the future. So. Thank you for your attention, and just wanted to shout out to my co-authors from GDM on the paper. Thanks.
Very nice talk. Let's take one quick question. There's anyone in the audience? Okay, if not, I have a question. So what do you think about like stuff that we can do in the pre-training stage for encouraging this kind of conversation skills?
That's interesting. I mean, I don't know. I mean, I guess the argument is really that we need a different type of learning. And so, if pre-training is going to be super scalable, and essentially is going to be imitation learning, I'm not sure. I mean, I think, it would be really interesting to think about more RL-style methods at pre-training time. And if you're willing to do that, then I think games like this are the right way to go. Yeah.